This strange 4,500-year-old piece of rock, known as Core 7, is ancient Egyptian. It's an exact cylinder and has strange lines scored into it, which are perfectly spaced. In fact, it's one continuous line.
Is this evidence for an even far greater civilization that had those tools that we have no historical record of?
This is the ancient Egyptian tube drilling core number 7, with its infamous groove pattern. Do these grooves form a spiral? Are they concentric circles? Is there maybe a third option? Stay tuned to find out. This video discusses the infamous Petrie core number 7, the subject of many theories and speculations, due to the peculiar pattern of grooves left on it after drilling. Today we'll find out if there's a continuous spiral in that groove pattern. Petrie's core number 7 is an ancient Egyptian artifact. It's a roughly cylindrical core left over after drilling, with a pattern of near-parallel grooves. It's kept in the Petrie Museum in London. It was discovered by Flinders Petrie in 1881 in Giza, in the mortuary temple of Khafra. The temple is located here. According to Petrie, he found the core in the south pivot hole of the doorway leading to the chamber with niches. The stump remained in the hole as it was hard to break out. There are several doorways leading to the chamber with niches, but it looks like only one aligns north-south, as opposed to east-west. This is presumably the location of Petrie's find. A core of this kind is the byproduct of tube drilling into stone or concrete. Tube drilling, whether modern or ancient, manual or mechanized, will leave behind a core. If the hole doesn't go all the way through, the core will remain attached to the original stone and will need to be knocked out of the hole after drilling. The core is covered in a pattern of wobbly, disjoint, but still nearly parallel grooves. What caused this pattern has generated controversy since the very beginning. Petrie gave his own views. Here they are. 1. Each groove was carved by an individual fixed jewel point harder than quartz, not an abrasive powder. 2. The grooves form a spiral. This spiral indicates a rapid rate of cutting into the stone under immense pressure. 3. Jewel points were set not just at the tip of the drill, but also on the sides, because the grooves are equally clear across the length of the core, not just the leading edge. The jewels mounted on the sides caused the tapered shape of the core. Petrie's view was opposed by the archaeologist John Evans. The astute objections of Evans established almost every single argument repeated today, in favor of loose abrasive having made the near-parallel grooves. Here are his comments. 1. The cuts could have been done with a tube made of copper with loose abrasive powder, such as corundum mixed with water. 2. Distinct near-parallel striations can be made if the abrasive particles, over time, tend to fall into already carved channels. 3. There is no substance on Earth which can cut into granite at the rate proposed by Petrie in a single rotation. 4. Even if such a substance existed, there's no way to affix it to a thin tube in a way that would withstand the huge forces proposed by Petrie. 5. The tapered shape, as opposed to a straight cylinder, doesn't indicate advanced technology, but the very opposite. Why? Because all the energy that goes into creating the taper is an unnecessary waste of the grinding effort. The advanced and efficient way to drill, as it is done in modern times, is to place the abrasive agent only on the very tip of the tube drill, so that the resulting core is as cylindrical as possible. We now jump to 1980s, when Gorelick and Gwinnett tested several types of loose abrasives to see what traces they leave after tube drilling into granite. Their paper always uses the ambiguous phrase concentric lines, which just means lines curving around some axis without specifying exactly how. But in one photo, they note an important distinction, which other claims either confuse or dodge. There's a difference between one single continuous line on one hand and many discontinuous line segments, which merge and split. We'll discuss this in detail later. As an aside, because their paper was published by UPenn's museum, it's often implied that they had worked at UPenn and that their views reflect academic archaeology.
In 1983, researchers at the University of Pennsylvania had reviewed one of these historical letter exchanges.
The specialty of the authors is actually dentistry. Experimental archaeology was their hobby. This doesn't diminish their paper, its claims are still judged on its own merits. It's just something that needs to be clarified. Interestingly, there's a connection between Petrie's core and dentistry. It may come up in some future episode. More recently, Christopher Dunn, in his book Lost Technologies of Ancient Egypt, said that he'd been unable to reproduce such near-parallel grooves with a manual drill and loose abrasive powder. Therefore, like Petrie, Dunn concludes that the grooves were made by some ancient drilling technology which could cut into granite with a feed rate of about 1/10 of an inch within just one revolution. As evidence of a spiral, Dunn and his proponents offer photos of cotton threads wrapped around the core, supposedly matching the grooves. This is not scientific evidence. This is an arts and crafts project. An online search will show plenty of photos of spiral threads wrapped around many things. Fingers, eggs, arms, house pipes, wine bottles, soda bottles, juice bottles, pill bottles, and unspecified bottles. These objects have no spirals on them, nor do the photos prove any. These photos only show that you can wrap a string around an object. In the photos of the core with a thread, we can't see the other side, nor what's under each thread, which could be flat spots. The right way to provide visual proof in such case would be as follows. If the museum allows stone rubbings, do a classic rubbing of the whole surface, showing all grooves. On the rubbing, use a thin red pen to draw the spiral you propose. If the museum doesn't allow rubbings, make a silicone mold, like Gorelick and Gwinnett, then use it to cast a plaster replica. Rub the replica with carbon paper, crayons, or chalk to enhance the grooves. Draw in your proposed spiral in thin red pen. Show the result from all angles. This way, others can see the choices you've made at each step. For example, if you're tracing this groove and you decide to continue it this way, you have to explain why this way, and not this way. The explanation must be objective, using physical laws or rules that apply in all cases. If you continue the line here only because the whole thing then looks more like a spiral, you're not showing that there's a continuous spiral. You're simply creating a nice illustration of classic selection bias at every such point. Before we even get to geometric analysis, let's first show the basic logical flaws in the claim. The first fallacy is a false dilemma. False dilemma is when someone tries to force two explanations where more exist. An example is a quote from Dunn's book, where he says that, after his inspection, he concluded that the groove pattern on the core is a spiral, rather than individual horizontal striations. Note the words, rather than, and a spiral, singular, that is, one continuous line. A single continuous spiral is given as the only alternative to horizontal striations. But it's not the case. Nature offers many examples of lines that are disjoint, that is, not continuous. Yet at the same time they revolve around some axis or point, like a spiral. In fact, in the case of fingerprints, it's precisely the discontinuities that let us distinguish individual patterns. If fingerprint spirals were continuous, we couldn't really tell different spiral patterns apart. In everyday English, people may call all such patterns spirals. But in a technical debate, like this one, the correct term for the cases shown here is not a spiral, which means one continuous line, but rather disjoint lines with a spiral tendency. By the way, nothing prevents the shorter line segments from joining locally and forming longer stretches. But it won't change the fact that such patterns start out as shorter disjoint lines, which emerge locally as a product of organic growth over time. This distinction is crucial in this debate, because disjoint lines with a spiral tendency are most often the product of non-manufactured, organic processes of growth over time. In contrast, objects with a single, regular, continuous spiral are typically manufactured. For this reason, objects with a single, regular, continuous spiral line are perceived as made by a machine. That's why, in this debate, using the ambiguous word a spiral, implying one continuous line, leads to unwarranted associations with machining. This table shows how the two aspects of the line pattern should be examined separately. We must ask two separate questions. 1. Is there a single continuous line on the core, or many shorter disjoint lines which sometimes merge? 2. Is the line or lines horizontal, or do they have a spiral tendency?
And this really is the meat of the argument that I've kind of exhaustively tried to expose here. It all comes down to helical versus horizontal grooves.
This is incorrect. It's the continuity of a line down the whole object that more strongly distinguishes machined or manufactured objects from other spiral patterns. The direction, horizontal versus spiral, doesn't tell you much. We actually do have examples of cylinders etched by a single jewel point, namely Edison phonograph cylinders. Here's a close-up of the grooves on such a cylinder. To human eyes, their spirality is invisible. The grooves look horizontal. On the other hand, here's the interior of an engine cylinder with a spiral abrasion pattern. A single-point tool can make almost horizontal lines. Random non-single-point abrasion can make spirals. The real distinguishing factor appears under a microscope, the continuity of the line. The particle abrasion lines emerge and end in random places. Sometimes they cross. The line on the Edison tube, carved by a single point tool, forms separate, continuous windings with no merging or diverging. Otherwise, you couldn't play the sound back. So in this debate, if someone uses the ambiguous word spiral, they need to clarify. Do they mean a single, continuous line down the whole object? Or multiple disjoint lines with a spiral tendency? This will prevent using the word spiral to create associations with machining. This is just a generalization. It doesn't mean that every object with a single continuous spiral is manufactured, especially if the spiral is irregular. The second flaw in the logic of such claims is to confuse depth with time.
This core seems to have been drilled out of solid granite using a rapidly rotating drill.
This machine turns at 1,600 revolutions per minute. How on earth could the Egyptians drill like this? Nobody knows. It's clearly impossible. And yet, they did it. The evidence is carved in stone.
This confusion starts with Petrie. When describing the pitch of the alleged single spiral groove, Petrie writes, "What also shows this enormous pressure is the rapidity with which the tool sunk into stone." The word rapidity is ambiguous. It could just mean that within one rotation we carve deeper into the material. It could also mean that it's done in a very short time. Unfortunately, Petrie finalizes his blunder by saying, "The cutting points bit deeply and cut off stuff rapidly." This contrasts deep with rapid by using the word "and" between them. In other words, now rapid means in a very short time. This is unwarranted. Even if we accept some proposed powerful single-point drilling bit, there is nothing about the core that tells us how long it took that bit to carve one spiral revolution into the material. For all we know, it could be seconds, minutes, hours, or days. To answer the questions we've raised, we need to analyze the spatial distribution of the grooves around the core's rotation axis. Doing it manually is tedious and error-prone. The right way to do it is with a 3D scan. The History Channel had the core laser scanned for its TV program, but they made no actual analysis of the grooves. The purpose of scanning was apparently just to awe a non-scientific audience with a red laser beam and imply that something scientific was happening, though there wasn't. Acquiring a 3D scan directly from the core proved impossible, so we created an accurate 3D model using photogrammetry and public sources. Here it is. We did not reconstruct the very top and bottom broken-off surfaces, as they play no role in the analysis of the grooves, which are on the sides. Here are a few comparisons of our model with some photos of the core. While we recreated the core's surface color and appearance, it plays no role in the analysis. It's the accuracy of the grooves that matters. This is assured by the recreated, very detailed topographic map of the core's surface. Tracing this map gives us the 3D spatial distribution of the grooves around the axis of rotation. Each groove is colored separately. For this analysis, we removed from consideration certain lines, such as boundaries between the component minerals in the granite. We can't know for sure if such lines are random or created by drilling. Since we're investigating the drilling mechanics, we have to accept only lines unambiguously left by drilling. Here's how to measure spirals, both a single continuous spiral and the spiral tendency of shorter disjoint lines. The relevant property is the lead angle. It's the angle between the spiral, or a helix in our case, and a plane perpendicular to the axis. The core is a vertical cylinder, so the lead angle is between the helix and the horizontal plane. Here's how it works. Let's say the core is covered in concentric parallel circles. In a side view, the circles look like horizontal lines, just like the green horizontal reference plane. If we zoom in, we can see that the angle between a circle and the green line is 0. Now let's say there's a continuous spiral, or helix, on the core. In a side view, the spiral looks like a zigzag at a slight angle to the green horizontal line. If we zoom in, we see that the angle between the spiral and the green line is about 1 degree, and the spiral winds 35 times around the core. How do you deal with irregular lines like the ones on the core? We divide each line into tiny segments, and we compute the average lead angle for all those tiny segments. What about wobbliness? The grooves randomly move up and down a bit. Fortunately, statistics will help. With a high enough sample, it's surprising how well the overall tendency is preserved. Here's an example. We can take our original concentric rings, then distort them up and down, even to the point of the lines crossing each other. Yet the average lead angle for the whole core remains close to 0, with a deviation of just a few %. Despite the wobbliness we've added, statistics lets us see the underlying pattern. Similarly, we can take our spiral, then distort it up and down, even to the point of crossing. But the average lead angle for the whole core remains close to the real underlying lead angle, again, within a few %. In both cases, the average lead angles remain sufficiently distinct from each other, so that despite the wobbliness, we can still tell if the underlying tendency is horizontal or spiral. We now have all the tools to detect any spiral tendency of the grooves on the core. So what's the answer? The grooves on the Petrie core have a spiral tendency. The average lead angle is roughly -1 degree. For a continuous spiral, it would correspond to a pitch of 2.9 millimeters or 35 windings. Note the caveat we made earlier. We've established a spiral tendency, not a single continuous spiral. Interestingly, the lead angle is negative. It means that the spiral tendency is counterclockwise, as seen from the thinner end of the core. This was not explicitly stated by Petrie. If the spiral tendency is related to the drill's rotation, it means that the drilling on core 7, had it been a one-direction drill, was done counterclockwise. Dennis Stocks in his book speaks of horizontal striations, but it doesn't sound like he actually measured them. Also, he generally uses a bidirectional bow drill with its own characteristics. It would take a bigger sample of cores to establish if, for one-direction drills, the spiral tendency and the drilling direction are related. By the way, Dennis Stocks could reproduce the striations, while Christopher Dunn, in his attempt, says he couldn't. Here's a histogram of lead angles for all groove samples. The variance is quite large. At the extremes, some grooves run almost parallel to the axis. Angles approaching 90 degrees are very peculiar. They imply that the hypothetical cutting point could pierce almost straight down into granite, like a needle, without even turning a spiral, which is rather hard to believe. Let's now check the continuity of the grooves. Let's say there's one continuous spiral wrapped around the core. If we rotate a plane around the core's axis and count the number of intersections with the spiral, it will be constant, the number of windings. This would also be the case for concentric circles, but we've already established a spiral tendency. So what happens if we do the same with the groove pattern? For reference, this is 35, the number of windings we expect for a continuous spiral, given the spiral's lead angle. But what we actually get are scattershot values ranging from 34 to 61. So why do we have nearly 30 extra grooves? If these grooves were cut by fixed-point jewels, there were many jewels carving completely useless grooves, not needed for a continuous spiral. Carving useless grooves is primitive technology, not advanced technology. Advanced technology minimizes effort. The windings count actually clusters around 48, though the lead angle requires 35. For a continuous spiral, there's an unbreakable mathematical relationship between the pitch, the lead angle, and the radius. If the average pitch between grooves doesn't match the lead angle, there is no continuous spiral, no matter how many cotton threads you wrap around the core. What's actually happening is the interplay of two mechanisms or processes. One spaces the grooves apart, the other one tilts the grooves slightly. We can say for sure that they're not linked in a way that makes a continuous spiral. The nature of these mechanisms is a complex issue. It may be explored in a separate episode. Here's what we found out. The grooves on core number 7 have a counterclockwise spiral tendency, with a lead angle of about 1 degree. There is no continuous spiral. The situation resembles tree bark with a spiral tendency. One growth aspect tilts the line slightly, another one dictates their average separation. These processes do not create a continuous spiral.